Okay, so welcome to this week's Origins Colloquium. It's a great pleasure to welcome John Mather to give the talk this week. John Corbett. John received his PhD from University of California, Berkeley, and then was um, working on a NASA's Goddard Space Flight Center, where, of course, his pioneering work on the Cosmic Background Explorer satellite gained worldwide attention with the detection of the primordial fluctuations in the microwave background. Groundbreaking result for which he was awarded the Nobel Prize in Physics in 2006. Then, in more recent years, he basically steered the James Webb Space Telescope project from 1995 until 2023, and its a great success is due, I think, in large part to John's great effort on that project. And so today, John is going to tell us about a range of astronomical instrumentation and what we can look forward to in the future. Welcome, John.
Well, thank you, Jonathan. Yeah, I want to tell you what might be possible for us in the future. So I've got here a little bit about the James Webb Telescope, but also I'm very interested in new technologies. I grew up in far northern New Jersey with books and dreams about great telescopes. So I'm still doing that. So I've always felt that the great discoveries would come from great equipment. So looking for revolutionary ways to make that kind of great equipment. So I think you're going to have lots and lots of stories about the Webb telescope, which I'm showing here as an example of great new technology. As you know, it's a 6.5-meter diameter deployable infrared telescope in space, operating around 40 Kelvin, with the detectors at that temperature and also at 7 Kelvin. To cover the infrared wavelength range from 0.6 to 28 microns. And as you know, it's been producing astonishing discoveries. The number of technological inventions that were required to make this happen is quite daunting. But fortunately, we had the ability to do it because our astronomical community came together and agreed that this was the next great breakthrough area of technology to produce breakthrough science. So even when the project cost a lot more than it was imagined and took a lot longer than it was imagined, it was still the one thing that could not be replaced by anything else. So we were able to keep on doing it. So thanks to enlightened legislative approval in Europe, Canada, and the United States, we're able to do it. So I'm going to, I guess, skip through a few things just to put a little context here. Big questions that I think are worth our attention. Where did we come from? And what is our cosmic history? Everybody wants to know, are we alone? And where are the neighbors? One that we astronomers can begin to work on is whether life will always occur given a chance, or whether it almost never occurs because it requires some very rare combination of something or other. So that's one of the reasons I've been interested in astronomy ever since I was a little person. So, as we know, Hubble showed us that the universe is expanding and distant things are running away from us at great speeds. Unfortunately, this was then named the Big Bang Theory by Sir Fred Hoyle, which has confused our public immensely because people think when they hear the words that it's a firecracker going off in a pre-existing space and time. And of course, that's not what we astronomers have seen. So thank you, Sir Fred, for making things mysterious that did not have to be. But all the same, it's wonderful and exciting that we get to track down the meaning of this chart. So here's the Cosmic Background Explorer project, COBE satellite that was mentioned in the beginning in the introduction. This was also new technology when it went up. It required a liquid helium cryostat there in the center, which was the second such cryostat ever flown. The first one went up on the infrared astronomical satellite, the IRAS, even before us. It had new instrumentation, cryogenic instrumentation with Fourier transform interferometer to measure the spectrum of the cosmic background radiation, a small infrared telescope to look for cosmic infrared background radiation, and finally it had new technology for microwave receivers to map the hot and cold spots, the anisotropy. And we had a new technology for a spinning stabilized spacecraft. So the spin axis of this observatory pointed away from the Earth as it orbited the sun, orbited the Earth. So quite a remarkable accomplishment of high technology to make something possible. And as we know, we made it work. Hubble was also new technology. It is now 34 years old, almost 35. Can you imagine that? And it is still working beautifully because it also embodied new technology, some that had been developed for the spy satellite business, and also new detectors that only astronomers really needed, but which we now have. So it's up there and still working because astronauts have been up 5 times to keep it going and repair it. We have the Webb telescope here with instruments that you'll hear more about from other speakers, and new technology everywhere on this one. Here are the major summaries of what we got there. We had to put this one out to the Lagrange point L2 area. We have seen the highest redshift galaxies so far, 14.3, and maybe there are more to be found a little bit farther out. We have been surprised in wonderful areas with the discoveries, but my perspective on this is, well, of course we were going to find these things if we built the new equipment. So thanks to our amazing engineering teams that made it possible, that about 20,000 people took to put that observatory together and put it up and make it go. And now there is something like 10,000 professional astronomers in the world, and at least half of them have already participated in proposals for the James Webb observing time. So just a quick reminder of what we saw. We saw this gigantic galaxy cluster in the middle, producing gravitational lenses to produce multiple images of even more distant galaxies. We have a handful of interesting but not very interesting stars here. But the pattern here tells us a lot about galaxy evolution, the structure of galaxies, the distribution of dark matter, and it's at least this general idea of using gravitational lenses to reach farther out in space and time has been extraordinarily powerful, as you know. A few lovely surprises just to come close up. This isn't exactly a cosmic origins, but local origins. We are now able, with this observatory, to map molecules on the surfaces of satellites of the planets. Here's hydrogen peroxide, and this is not the only example. NASA have sent a new technology observatory just recently to orbit around Jupiter and look at Europa, where there's could be signs of life in the water coming out from the blocks between the ice blocks. We have attacked an asteroid. We have watched it happen. Another new technology, precision navigation at extreme distances, has made that possible. Now we know a little bit about how to defend the Earth from killer asteroids. We have mapped molecules on Titan, and we will be sending a new technology helicopter out there to hop around to look at this details of the surface. This is a pretty astonishing capability. The temperature out there is only about 60 Kelvin or 50 Kelvin or so. So there are lakes and rivers and clouds of ethane and methane. So how do you fly a helicopter while you have a radioisotope power generator, and you have batteries, and you store up electricity for a while until you can make your little electric quadcopter fly around? We have launched, I should say, Europe has launched this small telescope, relatively small, 1.2 meters, to look for the dark matter and the dark energy. And as far as I hear, it is working very well, and we will have statistics on hundreds of millions of galaxies in a little while. But that was only just a little over a year ago that it was launched. We are constructing and finishing this even more astonishing telescope, the Vera Rubin telescope. And so we have the prospect of totally startling discoveries from it. Probably the biggest ones will be about the things that change every night. They expect something like 10 million alerts every night, 20 terabytes of data. So I think we should expect surprises as soon as they get it turned on. We'll be flying the Nancy Grace Roman telescope, another new technology. Here, the telescope part is not so new because we're actually using a used set of telescope optics, but we have new technology for the cameras. We will have about 100 times as much field of view as the Hubble Space Telescope, so we will be able to survey enormous amounts of sky in a short time. We're also carrying a coronagraph, another new technology item to hunt for planets around other stars. Probably not capable of seeing an Earth around a sun, but you never know. We certainly have to go try. So what do we do to find new things? Well, as my story has been very similar to what Martin Harbutt told in his book, Cosmic Discovery. Build new equipment and new things will turn up. So I like to change on Carmen's quote to say, build the tool that was never built before to discover what was never known before. So how do we do it? Well, we have to have an idea. If we could build a new tool, and then we have to find somebody that could help us build it and propose it to NASA or NSF, or if you're in Europe or Canada or China, to various other sources of resources. So how do we do this? Well, of course, in the US, we have the decadal survey, which I like to call a giant science party. We have hundreds of people meeting and coming to agreements of some sort about what they think we should do next. And the remarkable result of this is that Congress and NASA are able to say, okay, astronomers made up their minds. If we fund this, we will be happy. So this has been going on since about 1960, I think, with these kinds of gigantic survey books. And the result is spectacular. International agreement is possible and very powerful. So you can read these books. They're all available. So the thing that we've said we wanted to do next is called the Habitable Worlds Observatory, or Observer. It's about the size of the Webb telescope, only much more perfect, so that it is capable of having a coronagraph on board, able to see an Earth-like planet orbiting around a sun-like star. So I think it might not be as hard as people have thought in the past, because this telescope does not have to be cold like the Webb telescope. So we shall see. People are starting to think about it. We can't put serious work into it until we are finished working and launching the Nancy Grace Roman telescope. But there will be a possibility that this could happen in 20 years or less. That's what I'm hoping. So what else can we do? Well, there are many, many other things happening. I wanted to point out that there are laws of correlations, at any rate, about how rapidly things can grow. Moore's laws, everybody was very aware of that for processors. It's slower now, but we have an immense market. There are basically 8 billion customers for computers now, almost, and there's a $1 trillion budget a year for whatever it is that we want to build. Other things are also going up in frequency, and so costs are coming down just because the host of tiny incremental improvements that grow into gigantic improvements. So have ambition, have faith that in your lifetimes, much more powerful observatories will become possible and affordable. And with any kind of luck, our world economy and our world society will be able and interested to support them. So what's coming up? Well, things are growing very rapidly in many areas: detectors, mirrors, particle detectors, gravitational wave detectors, adaptive optics, fiber optics. We can even make spectrometers on a chip for millimeter waves, and some are even growing into the fiber optic versions of spectrometers. We have a large number, maybe a too large number, of small satellites for the communications industry, but pretty much whatever you can imagine, you can almost build it. So have imagination, go for what you think might be possible, and it may be. So just some examples of surprises. Here is a dark matter camera. It's a collection of commercial camera lenses with really excellent detectors, and they're able to find objects such as this one, which seems to be 99.99% dark matter. Do I believe this? I'm not quite sure. But at any rate, this was not incredibly difficult. This is something ordinary people can do. That is to say, astronomers. Everyone knows about LIGO and the discovery of large numbers of gravitational wave events. This was a new technology which actually required dozens of new technologies being pushed to the ultimate limits, and it was made possible by brilliant people and also by the sort of persistent faith at the National Science Foundation that this was worth doing, even at the great cost that it would take. We are on the cusp of significant advances in very long wavelengths, the gravitational waves. I believe there's already an announcement that we have information about the spectrum of very low frequency gravitational waves from the pulsar timing. So this is something you might not have guessed if you didn't know it was possible. We have the TESS observatory up there, which is already observed many thousands of targets, and I'm not sure whether we're still running it, but it has done a wonderful job. Another thing that's small, relatively small, but extremely productive. We are looking for dark matter in laboratories. Now, I'll show this beautiful picture. I guess we have to admit that no dark matter search has yet been successful. So we know a great deal about what dark matter is not. But we do know that it's doing something out there, and astronomers, that's to say us, are the only ones so far who can tell you anything more about it. So let us go look at those images of galaxies and galaxy clusters and find out what's really behind them. Here's another dark matter search, another laboratory project, hundreds of kilograms of xenon. So one of these days, somebody might possibly find a dark matter particle. Mostly, but you just never know. I have no opinion about whether we will or not. Oops, I did that one already. We have a laser interferometer going up into space in a little while. 2034 is not so far off. And that will be capable of measuring gravitational waves at lower frequencies than could be seen by LIGO. So these are lower frequencies, meaning objects of significantly larger scale, larger mass, larger size. And nevertheless, the technology in question is tabletop. It's just that you need to get it into space. Something you might not have been thought possible, we have the ability to make X-ray telescopes of much better angular resolution and sensitivity than what we've had before. Here's an example. Our colleague here at Goddard Space Flight Center developed a way to make single crystal silicon mirrors for X-rays. So, of course, as you know, X-rays cannot be focused, but you can reflect them at grazing incidence, so that drives the particular geometry here. But this is a matter of engineering and ideas about how to support these silicon crystal mirrors. So we can do this. How soon we do it depends on how important it is to you, all of us astronomers, and as combining with some progress in the technology. We can split atoms and use them for measuring things. And by this, I mean split atoms as we do light waves. I've been working with teams of it on this because there was a hope, and still is a hope, that we could use these atom interferometers to measure gravitational waves. So just to give you a hint about how you do this, well, first you have to use a magneto-optical trap to produce a collection of atoms that cool down to nanokelvin or picokelvin by slowing them down with laser beams and magnets. So then after you've done that, then you can do something to them with laser beams. If you hit an atom with just the right amount of intensity of a laser beam, you can give it a probability of 1/2 to be in an excited state. And if it is in an excited state, it has received some momentum, and it will go somewhere different from if it did not. So you now have the ability to build something like functions exactly like a Michelson interferometer or a Mach-Zehnder interferometer. So you have two pieces of the same atom going in different places, and then you can bring them back together again with additional laser pulses and make them interfere. So now we have atoms in space subject to disturbances by other forces, gravitational forces in particular. So now we can measure whether the object has been rotated, whether it has been accelerated, whether there's even a gravity gradient. So this is something that is in development, and many wonderful things have already been done. And astronomers are not the only ones who care about this. Military have invested a fortune in miniaturizing all of these kinds of equipment because, of course, you need to be able to navigate when you cannot see the GPS system, either because you're a submarine or because the GPS system is broken. So there are now miniaturized atom wave interferometers being built for other government agencies with 3 letters. So those are possible. The spillover into astronomy and physics is that technology has been developed and is being developed that will enable us to do many new things. And I think eventually we may even be able to find gravitational waves with them. In the short term, there's a pretty significant likelihood, I think, that we will have them in use for measuring the changes of the shape of the Earth's gravitational field from space. And this is important for understanding the motion of water. Water moves around on the Earth because of wind and clouds and water flows that you already can see, but also because people pump the water out from underground to use it for watering the crops or drinking. So we're able to measure the changes of the gravitational field of the Earth from a space using gravitational detectors based on atom wave interferometers. So who knew, but it is now possible. This is just another chart that said other people need this too. Laser-based quantum gyroscopes are being developed as well. So this particular claim comes from Europe that maybe it's not impossible to have tiny ones. It's not impossible to have Fresnel telescopes. So that is to say diffractive telescopes. So how would you have a diffractive telescope? You basically make a structure, just like a Fresnel lens or a Fresnel with its rings across it. And if you really try, you could make a structure to image X-rays or even gamma rays by diffraction. So to do this, it basically means formation flying of 2 spacecraft, one with a lens and one with a detector. So as long as we can learn how to do that part, we will be able to achieve extraordinary angular resolution for X-rays and gamma rays. So there are possibilities for you to learn more about the physical structures of compact objects. We can build bigger telescopes in space too. Webb telescope is 6.5 meters. Here is a sketch showing one 30-meter space telescope was studied by Bill Ogerle and colleagues here at NASA Goddard. It shows you that it's not impossible to imagine something this large. Nobody's saying this is easy, but as time goes on, we may be able to do this, particularly as robotic assembly becomes possible. So to do this, they imagined ultralight structures, and you can see then rather gossamer kinds of things. But why not? So now I want to talk about space-ground hybrid observatories. There are things we could do with a telescope on the ground and something in space to make it work better. So various possibilities here. We could photometric calibration, adaptive optics for astronomy and for the sun. We can do it for imaging interferometers, for the millimeter waves. I will even show you a sketch for an orbiting star shade. There's a possibility to extend the Event Horizon Telescope into space to get much better images of black holes. So I'll just sketch for a few minutes some of the things that we've been thinking about in this area. So here's the Event Horizon Telescope. It's a consortium of observatories on the surface of the Earth, and we can get the image on the left as of 7 years ago. Now we know what the next thing to do is to make an extension into space with an orbiting millimeter wave dish and bring back the data by a laser beam to the ground to combine with those others. And we could get much, much sharper images of those photon rings and actually determine the spin of a black hole directly from the way the photon rings are distributed and distorted by the spin of the black hole. So who knew that that would be possible? But it is possible. We can do better photometry. So why do we care about photometry? Well, some of the things we're doing depend very directly on knowing the brightnesses of things. So for cosmology, for instance, to know the dark energy terms, so we need to compare the brightnesses of standard candles at different redshifts. So that means we have to have the ability to say we know their spectrum exactly, and that our instrumentation spectrum, instrumentation's correctly calibrated of sensitivity versus wavelength. So we are already doing a study at NIST with that, and there's also a 12U CubeSat that's been approved for Phase A study at NASA by NASA. It's called the Landolt mission, named after Arlo Landolt, who was a pioneer of photometric calibration. So these things are becoming possible, and they're not so impossibly difficult. A CubeSat in the pioneers NASA jargon is just tens of millions of dollars and not hundreds or billions. So much is possible with photometric standards. So if you could do this, we could have a much better knowledge of the cosmic dark energy. And also, of course, know something more about exoplanets, because we depend on knowing how bright their stars are to know how bright and what are the conditions on the planets. So now skip over that. Now I want to talk about large telescopes and extremely large telescopes. So this is a lovely diagram showing sizes of telescopes. When I was a child, we had the Hale 200-inch telescope, about 5 meters. Now we have much larger ones, 10, 12-meter telescopes scattered around the world, in Texas, in South Africa, in Palma, on Keck observatories on Mauna Kea, South America. We have large telescopes, and we are about to have much larger telescopes. The European Extremely Large Telescope is coming along, 40 meters in diameter. It's hard to imagine something so large, 6 times the size of the James Webb Telescope. And of course, the two American-led teams for the 30-meter and the Giant Magellan. There's also coming along, not nearly as far along as we wish, but they're coming. Now, there's a sort of indication here on this lovely graphic that could be a 100-meter telescope. It's called the Overwhelmingly Large Telescope, or OWL. Of course, we're not building that one yet, but it's not impossible. It's not time yet. We have to build the smaller ones first. So how do you make full use of these gigantic telescopes? They're just light buckets. We should be able to use adaptive optics on them. So here's the sketch showing how adaptive optics works. And by the way, the right-hand one points out that if you go to the eye doctor, they have adaptive optics in your eye doctor's office, but you never just hear about it. They just look at your eye and say how you're doing. But we astronomers want to do this very well, and we would like to do it on the largest possible telescopes. So if you could do that, then it would be spectacular. So how could you do it? One way is called single conjugate adaptive optics with a target near the field of view that you want to see. It's a relatively straightforward algorithm. You need a bright star near the target, um, and we already have that kind of thing working. But right now, we have a lot of problem with the glare from the target star that we use for the adaptive optics. It spills out everywhere. Um, if you had a laser star in space, an actual laser shining down from above, you could get rid of its glare with a wavelength filter. So we could do that. We could have adaptive optics, diffraction limited performance on all those telescopes I just showed you, and it would be extraordinary. So there's a huge speed advantage if you can do this. The speed advantage for observing a point source scales as a fourth power of diameter. So that means that, say, the European telescope at 40 meters diameter compared with the Hubble telescope at 2.4 meters diameter is many thousands of times faster if you can get the diffraction limited performance. So let's see what it takes to do that. So here's an example showing that visible wavelength band is the right place to push this. This is a map of the sky background brightness versus wavelength. You see that the infrared sky is very bright, beginning around 0.9 microns due to air glow in the upper atmosphere, and then at 2-something microns thermal emission as well from the telescope itself and the atmosphere. So let's see if we can push the adaptive optics to the visible band. Well, of course we can. That's what we should try to do. So let's do that. This is the thing to work on. So you could do everything that you currently do, only better, with a visible wavelength telescope. So how can you do this? We have been working on what we're calling the ORCUS, the Orbiting Configurable Artificial Star. And here's the sketch showing a small satellite beaming its laser down to the Keck Observatory. And we've studied how to do this. We know how to do this. Basically, it takes a very ordinary laser beam, a very ordinary small satellite. We know how much it costs. And for less than 100 million, you could get a whole system, including the satellite and the adaptive optics, all working. The same satellite could work with any telescope. So there is a thing for you all to think about, a new generation of observatories on the ground working far better than they've ever worked before. So we've recently had a demonstration showing that you could resolve the volcanoes on Io with adaptive optics from the Keck Observatory at visible wavelengths. It's quite spectacular. I don't have a picture for you yet. We will be able to use these interferometers that we've built on the ground. Here's an example of one. This one will be able to get 100, does already get 100 micro arcsecond angular resolution. And this is a very difficult object to use because there are not very many sources that are bright enough to do this technology. However, if you had an orbiting laser guide star, just like the one I just showed you, this observatory could see things that are 100 or 1,000 times fainter than what we're able to currently observe. And that would open up a whole new territory of high-resolution astronomy. Already one such interferometer produced a Nobel Prize for the VLTI gravity instrument, studying the black hole at the center of our Milky Way galaxy. So there's a lot of gold in this territory. I think we should be continuing to work on it. We can even use the similar technology to observe the sun. We already have adaptive optics working on the photosphere of the sun, and this is the most beautiful image of the sun. But you cannot observe the corona this way. If you had a laser beam coming through from near the sun, you would be able to focus a telescope on the ground, this very same one, and be able to observe the solar corona with the same angular resolution, about 25 kilometers. Should be maybe 100 times better than what we currently have. So it's something that we should be working on. So this now I'm going to conclude with my most radical story. If we could put up a star shade to cast a shadow of a star onto the telescope on the ground, then we would be able to see that picture on the right-hand side in a minute. A solar system seen at a distance of 5 parsecs with Earth, Venus, and Mars quite clearly visible in image. Now this is hard. This requires a 100-meter diameter star shade. It has to be 170,000 kilometers away, and it is not currently possible, but I would say it is not impossible. So if you could do that, you could get a spectrum of Earth. You see the blue curve at the bottom with spectra of oxygen and water showing up quite clearly, even after accounting for the interference of the terrestrial atmosphere. So there's a lot of possible science in this territory. So let me conclude here by saying we can do this. Our astronomy budget is small compared to the technology basis that we're depending on. So we can do this. So have faith and can keep on going. And here's our crystal ball. So let's open up for discussion now. And thanks for coming to hear the stories.
Thank you very much, John. So, yes, we have plenty of time for questions and discussion. And if you're there in Virginia, maybe Morsten can help me if there are questions, and Maya in Chalmers. If you're in Zoom, of course, just raise your hand. Well, I have lots of questions. Maybe I can start while we're waiting for one to come along here. I mean, the future of very big telescopes and whether they should be on the ground or in space, I guess I'd be curious about your opinion. They seem to be getting more difficult on the ground, and I think things scale, the costs and things scale also with quite a large power of the diameter of the mirror, and then maybe some, the effect of earthquakes and gravity and so on. Do you have an opinion on whether the future for the very biggest things is in space, or we can do things from the ground? How big can we go from the ground?
Oh my goodness. Well, on the ground, 40 meters that we're building now is about the limit that people think we can manage for now. Because there's sort of no avoiding interference from the wind and the gravity and the weather. And so you do need something similar to what they're building. So much bigger is much harder. And I think there's no way around it. The 30-meter telescope I showed you in space is not currently possible, but it's not heavy. Does not have to be heavy, because in space you do not have the same disturbances of gravity. So I think there are possibilities for very large things in space. But
Mhm.
right now it's a little hard to see that far. It depends on robotic technology that is still under development.
Mhm. But there was, I guess, there have been quite a lot of studies for the owl, the 100-meter telescope from the ground. Did those studies conclude it's there are challenges which are just not surmountable at the moment, or if ever?
Yeah, I think it's just too hard. But after we get the European ELT going, then we'll
Hmm.
be able to say, well, we've solved those kinds of problems. How much bigger could we build it?
Hmm. Hmm. Well, then I know from the James Webb experience, the micrometeorites cause some issues as things get bigger. Do we foresee more issues there, or is that a surmountable problem?
Well, that's an interesting challenge. You can't stop them unless you have a tube around your telescope. So the Habitable Worlds Observatory will have a tube of some sort to protect the mirror.
Hmm.
It needs much better mirrors than the Webb requires.
Hmm. Hmm. But it might be a concern for the very, imagine, enormous telescopes free floating in space.
Yeah, well, for not everything requires a perfect mirror.
Hmm. Hmm. Great. I see a question from Brant first then.
Hi, yeah, great talk. I just had a question because you mentioned having the lasers on satellites for adaptive optics and the possible future of sunshades. And all these are quite interesting, but I'm just kind of curious, along with the launch of a lot of satellites for internet and other things like this, is there worry that we would be sacrificing the amount of space in orbit to kind of make the ground space telescopes better, rather than trying to launch things that go a bit further out in space than as space telescopes?
Well, good question. The the interference we get from the Starlink and other internet satellites is basically because there are so many of them and they will go across your field of
Yeah.
view sometime. If your field of view is large, as it is for the Rubin telescope, then you'll see them all the time. If your field of view is small, as it is for a giant telescope doing adaptive optics, then you probably not see them most of the time. So I think the way is clear for continuing the adaptive optics program.
Thank you.
Because the laser satellite you discussed, John, you're imagining just a single satellite or a constellation that would be like a facility that could be used by a whole network of ground-based telescopes.
Yeah, well, one is good and many more is better. So you could have basically one in each area of the sky. The orbit requires a long ellipse. You have to place the satellite in front of your target. So then that means you have to maneuver the satellites to be in front of your special targets. And it's a little bit different maneuver for each observatory. But yes, once you show that this is a good idea, then I think everybody will want one.
Mm-hmm. So it doesn't sit in geostationary orbit then.
No, it's not geostationary. We call it astrostationary.
Ah.
Uh, you need to have a very long ellipse so that the orbital velocity matches the rotational velocity of the observatory around the Earth. So it's about 400 meters per second, which is very small compared with uh, the velocity at geostationary even. So it has to be much slower than that. So long ellipse, an astrostationary orbit.
Okay, that makes sense. Great. Any other questions online? Please feel free to raise your hand. Otherwise, let me ask then next about the moon. We've had discussions, or it's been mentioned, I think, in previous seminars in our series about possibilities from the moon. And I wonder if you
Yeah,
on that.
I know there's one thing that you cannot do any other way, and that's long wavelength radio astronomy. Um, the Earth is very noisy. The sun is very noisy, and there's only one quiet place in the solar system, which is the far side of the moon at night. So that tells us what to do if we really want to discover things in that wavelength range. I think there is a lot of possibility there. Um, Other things that people have talked about are the moon has fewer advantages. For instance, yes, you could build a spinning liquid mirror telescope on the moon, but you can only point it up. So that's a relatively small amount of sky that you can cover. So their interferometers are possible on the moon. They're hard to do in space. They're hard to do on the ground. They're hard to do on the moon, but it might be that there's an opportunity there. I think there is. For instance, astrometry. Astrometry to look for exoplanets is a wide open topic. We have not found Earth-like planets that way. We hope to. We had the SIM mission was a NASA project, which we were going to do, and it would have found many, but we didn't do it. So maybe there's a possibility for doing it on the moon.
Right. I
I've
remember.
seen some very convincing ideas on that one.
Uh-huh. Okay, very good. Again, if you're in Zoom, just raise your hand. I'm going to keep going. If there are no other questions there, let me check with Motion and Devesh there and Maya.
Yeah, I have a quick one, please, Professor Mehta. A silly one, really. So you just mentioned at JWST, the furthest galaxy we see now is at 14 redshift or so. I'm more curious about these population-free stars. I mean, should we be seeing them already? I guess not. But are there any other plans, new telescopes that we have in mind that can maybe like look at the spectra more carefully and distinguish carbon 12, carbon 13 lines and other things? Like, where are we in that regard?
Okay, on the search for the earliest objects, well, what we do now is we take a picture of a large field of view, and we look for objects that are very red, and then we look to see do they have the color that says, okay, all the ultraviolet light from that object has been blocked by intergalactic hydrogen. It's called the Lyman break. If we find an object that has that, then we go study it more and get a spectrum. So then we see a spectrum of a very early object. And we've seen a few that have very little sign of heavy elements in them. So we're getting closer to those very early objects. But also, I think we have to appreciate that the first generations of stars are massive, and they happen very quickly, and they burn out very quickly. So within a few million years after the first ones are born, then the neighborhood is filled with debris of heavy elements. So finding those very, very first objects is pretty tricky. And observing them remotely from a distance of 13 billion light years is pretty hard. So obviously the other path is to look for stars that were born in those earliest days but are still here. So very low mass stars that have almost no heavy elements in them. So we've got the two tracks, and ideally we'll find some way to understand the competing kinds of evidence.
Right. Well, let me follow up on that because I think many models of the actual, how bright these very first stars would be indicate that it's difficult for James Webb currently to see them. That they're probably at higher redshifts than 14, and even if they're massive stars, they're quite faint still. So what is the hope to push the sensitivity? What's the first facility that's going to improve sensitivity in this regime here? I guess in the infrared.
Right now, I don't think there's anything that we have in mind. To see the very first objects, you have to be looking at the infrared, because even redshifted Lyman alpha at redshift of 14 is that's 1.8 microns or so. So you need a telescope that can see that wavelength. We might have a little bit of a chance to see some of them from the ground.
Right. So the ELT in the K band with adaptive optics working, can you remind me is it sensitivity beating James Webb at those?
I don't know at that point. It's going to be a bit of the challenge is obviously the sky is very bright.
Mm-hmm.
So on the other hand, the fourth power of diameter is very large factor. So my guess is that what we'll have to do is try it. As soon as we have the equipment, we'll have to point at those highest redshift objects and see what else can we find.
Mm-hmm. Mm-hmm.
The ELT, you have to know where to look, because its field of view for adaptive optics is not that large. But we'll see. It will be very powerful new equipment, and we'll have the best possible adaptive optics. And it'll be working at near infrared much sooner than it can work in the visible band.
Yeah.
So, of course, what we do is when somebody's got something exciting, we all try to find it.
Right. I mean, ELT in principle should be online within, just several years from now. Is that right?
I don't know the timeline, but they're building.
Very good then. Any further questions? If not, let me come back to this atomic gravitational wave detectors that you mentioned briefly. You didn't have time to get into the details. I'm trying to understand. So these are atoms interfering with themselves, are they? And which then somehow you set up a system of these atoms in various states that is then potentially sensitive to gravitational waves. What frequency waves would be the ones relevant to here?
Okay, well, the frequency of waves you can measure with this depends on what's the spacing between your detectors.
Mm-hmm.
So, as well as the raw sensitivity of the detectors themselves. So, the thing you can build in a box is a gradiometer. It tells you how much more was the gravity at one end than the other. And so but now you need to have two or more of them spaced by tens, hundreds, or thousands of meters. So there are various versions of these you can imagine putting into orbit around the Earth. Um, so it would be, if you could do that, it would be intermediate between LIGO and LISA.
Hmm. But let me understand now here. So if it's just the spacings between the detectors, then why is that different or better than having using lasers? What's the
Uh,
advantage in the atomic?
well, the raw sensitivity of the atom wave interferometer can be very extraordinary.
Uh-huh. So the frequency range would be similar to either if it's a LIGO based,
Yes.
a ground based thing, or a space constellation like Elisa, but it'd just be more sensitive.
Yeah, it touches a different frequency range, according to how you a different frequency range for the gravitational waves.
Mm-hmm. Mm-hmm. Well, that's very interesting. But is that technology, I mean, if you had to guess how long it might take for that to mature to the point
Uh,
of.
well, the next space case will probably be, I think it's possible in the next 10 years, it will have an Earth observing gravity gradiometer,
Mhm,
which will demonstrate space qualification of the basic idea.
mhm,
And so then, assuming progress on the sensitivity, we would then know what to do next for gravitational wave surveys.
mhm, mhm.
By the way, there's a range where there's a cosmic background of gravitational waves coming from uh, pulsars and and from white dwarfs and various other spinning objects out there.
Right. No, there's a lot of sources to go for. Great. Well, let me see then. The thing the topic you ended on was looking for taking images and spectra of Earth-like planets, and so you showed a case of imaging a system equivalent to our solar system at 5 parsecs. So let me try and understand how there are not so many systems, right? I guess Habitable Worlds Observatory will go after these systems first. Is that right?
Yeah, they'll go. Because that's a multi-purpose facility that the whole astronomy community wants, I'm pretty sure we're going to have it. What's a little less known is, well, how good is it going to be for exoplanets themselves? One of
Mm.
its many scientific cases. So if we're lucky, then it is already good enough to see a spectrum of an Earth-like planet, like I showed you. Um, if it doesn't work so well as we hope, or if we can't finish it, and then we may try a star shade. You could have a star shade that would work with the Habitable Worlds Observatory itself, also.
Uh-huh. So
And
the
that
same
could be
as,
pushed. We might need that, for instance, if we decide that ultraviolet is the place to look, because we cannot make a good ultraviolet coronagraph, but we could make a good ultraviolet starshade, and it doesn't have to be so large.
hmm. Well, you mentioned that currently it's not technically feasible to make such a star shade. So what is the current bottleneck?
Well, it's just enormous. 100 meters diameter is as big as two football fields, and we need to have the mass quite small because we have to push it around in its orbit.
Mm-hmm.
So we've had a few studies trying to explore how could you make the 100-meter version, and it's, well, we shall see. I put in a proposal to NASA for an inflatable one. We shall see if they like it.
Ah, well, that sounds exciting. Very good then. Any last questions or comments to John?
Well, let me wind up and say I think that orbiting laser guide star is the next thing after the photometric calibration, and we are beginning to develop international cooperation plans. And so I invite people that are interested and want to help push that forward to get in touch with me.
Very good. Well, let's thank you again formally. So thank you again, John.
Thank you for the invitation, Jonathan.
I'll stop the recording.